We'll get started then. Uh, so, worksheets 23 through 29 and homework number 4 are due on the 2nd. Our last exam on chapters 23 through 29 will also be on the 2nd. That's right after Thanksgiving. Our presentations and our papers are going to be due on the 4th. So make sure your topic has been accepted. It's a 2 to 3 page paper on the topic and a 48-minute presentation on the topic. And the presentations will be on from December 4th to December 11th in class. The schedule of presentations is up on Brightspace now. Sorry it wasn't up earlier. I forgot to unhide it. I had it done a while ago, I just forgot to make it visible. But it's visible now. It had a small mistake on it anyways, which I just fixed, so. Presentations should, you should be aiming for a 48-minute presentation on your topic. So I've scheduled 10 minutes per person. Roughly. I've never had people run overtime, so I'm not worried about that. So let's get back to talking about normal and active galaxies. So we'll start by going over the types of reviewing the types of galaxies. We started talking about this last time, but there's been a bit of a break. So our deepest image of the universe show a great variety of galaxies. Some of them are billions of light years away. This is the Hubble Extreme Deep Field. This was this weirdly brilliant idea of, let's take the Hubble telescope and point it in a dark spot in the sky until we see something and see what we see. Like, I can't believe I actually managed to get the time to do this because, like, it was a long commitment and Hubble time is precious. But so a galaxy's age, its distance, and the age of the universe are all closely related. And thus the study of galaxies is intimately connected with the study of, in many ways, the study of cosmology, the study of the structure and evolution of the universe. In many ways, galaxies are sort of the basic unit that stuff forms in the universe. So what patterns do we find among the properties of galaxies? Well, there are 3 types of galaxies in Hubble's classification. Well, 3 or 4, depending on whether you separate spiral and barred spiral. So there are elliptical galaxies, which are round. The roundest ones are E0. The most stretched out are E7. I think it goes up to 7. There are spiral galaxies and barred spiral galaxies. The ones with the biggest bulge and the tightest bound arms are SA, smallest bulge, loosest arms are SC, and SBA and SBC. And then lastly, there are irregular galaxies. Irregular galaxies don't fit in this class, they're the etc. category. So this is an image from the Hubble Ultra Deep Field showing all of these specks of light are all distant galaxies. Here, for example, is a spiral galaxy from the Hubble Deep Field. This, up here, is an elliptical galaxy. Spiral galaxies have spiraling arms. Elliptical galaxies are round. And here is an irregular galaxy. It has it's neither spiral nor elliptical. It's got some weird shape. Most irregular galaxies seem to be recently involved in collisions. It is a common situation. So Hubble classified galaxies based on their appearance. Elliptical galaxy, and he made this tuning fork structure that he thought had something to do with the evolution of galaxies, but to our best current understanding, it does not. It's just a convenient way to organize galaxy types. Elliptical galaxies were on the single arm, and spiral and barred spiral galaxies on the double arm, with lenticular galaxies in between. And if you're talking about galaxies, lenticular galaxies are sort of in between elliptical and spiral. They don't have arms, but they are flat and disc shaped. But otherwise, they're a lot like elliptical, so it's sort of in between. Irregular galaxies don't fit any other classification, so are just sort of not on the tuning fork. So spiral galaxies have a distinctive spiral or pinwheel structure. They consist of a disk, a central bulge, a halo all around, and spiral arms. They have distinctive spiral arms. Spiral galaxies have ongoing star formation in those arms. Emission nebulae and open clusters show that star formation is occurring in the spiral arms. They have a population of old stars in the bulge and in the halo. So that implies that star formation has occurred over an extended period of time. So that is both young and old stars. And they're classified based on the size of the central bulge. So SBA has the biggest bulge, SBC has the smallest bulge. And SA has the biggest bulge, SC has the smallest bulge. SB would be the equivalent for barred spiral. Barred spirals are like spiral galaxies, except they have a bar in the center. Our Milky Way is a barred spiral galaxy. They have similar properties to normal spiral galaxies. They have a bar running through the center of the galaxy. The spiral arms come off the ends of the bar. Why the bar forms is not fully understood, but about 2/3 of spiral galaxies have this bar. It's very common. Here are some examples of barred spiral galaxies. This is an SBA, an SBB like our Milky Way, and an SBC. So the size of the bulge again determines A, B, and C. We use lowercase spiral galaxies are given an S to represent spiral or SB to represent barred spiral. And the galaxy classified as SA and SBA will have the largest bulge and the most tightly wound spiral arms. The galaxies classified as SC or SBC will have the smallest bulge and the least tightly wound spiral arms. And the Milky Way is an SBP, right here. Elliptical galaxies are round, they're ellipsoidal, but they're ball shaped. They're spheres or squashed spheres. They have no trace of spiral arms or a disk. They have no particular dust or young stars or emission nebulae. They tend to be old stars. They have a wide range of sizes. Elliptical galaxies consist of both the biggest galaxies, giant ellipticals, and the smallest, dwarf ellipticals. And they're round. And they have no spiral arms, no disks. They come in many sizes. They contain very little, if any, cool gas and dust, and show minimal star formation. And many do, however, have large clouds of hot gas extending far beyond the visible boundaries of their galaxy, which indicates something may have happened in the past. For elliptical galaxies, we use the letter E, and the numbers 0 to 7 are to specify how squashed the galaxy appears. E0 is a sphere. E7 is a highly extended ellipsoidal shape. It's like a football. And various galaxies come in between. So here are some examples. Here's an E1 galaxy. It's almost spherical. E4, it's more stretched out. E5, it's a little more stretched out. E7 is the most stretched out. And irregular galaxies do not have a regular shape. They can look like this. They contain cold gas and dust and generally contain significant amounts of star formation. They contain populations above they have population 1 and population 2 stars. They have a mixture of stars of different ages. And they're classified as IRR for irregular galaxies. So irregular galaxies have funny shapes. A lot of them are found a lot of irregular galaxies show evidence of collisions. So irregular galaxies have a wide variety of shapes. They tend to appear to be undergoing interactions with other galaxies. And those interactions cause bursts of star formation. So irregular galaxies also tend to be pretty bluish because they have lots of young new stars. So here, for example, this is a galaxy that another galaxy flew through, most likely. And you see this splash of star formation. Here's another irregular galaxy. And then lastly, there are lenticular galaxies, which are sort of in between spiral and elliptical. They're disk galaxies, but they don't have any cool gas or dust. So they don't have minimal star formation, they have no star formation. And they have properties that are like both spiral and elliptical. They're sort of in between the two. And they're classified as SB0 or S0. Generally, you see them as S0. So they're disc shaped like a spiral galaxy, but they don't have arms. They don't have any active star formation. So here's an S0, here's an SB0. The bulge is a little wider here. They have a disk and a bulge, but no spiral arms and no interstellar gas. And originally it was thought the Hubble classification was evolutionary, that galaxies might evolve from one time to another. It was thought maybe you'd start with a round elliptical and get flatter and flatter, become lenticular, and then become a spiral. How could an elliptical galaxy find cold gas and dust to become a spiral? Could a spiral uncollapse to become an elliptical? We do now believe that galaxies evolve, but that process is not anything to do with Hubble's structure. It instead involves collisions. So galaxies will collide with each other, change, they can merge, and that's happening even to the Milky Way, is currently cannibalizing a few small galaxies that are orbiting around it, and is on a collision course with the Andromeda galaxy. So they will eventually collide and merge into the Milky-Andromeda galaxy. So here is sort of a summary of the different types of galaxies. For spiral and barred spiral galaxies, they have a highly flattened disk of stars and gas containing spiral arms and thickening to a central bulge. And SB galaxies have an elongated central bar of stars and gas. Their disks contain both young and old stars, while the halos consist of only old stars. The disk contains substantial amounts of gas and dust. The halos contain little of either. There is ongoing star formation in the spiral arms, and gas and stars of the disk move in circular orbits around the galactic center, while halo stars have random orbits in 3 dimensions. Elliptical galaxies have no disk. Stars are smoothly distributed throughout an ellipsoidal volume. There's no obvious substructure other than a dense central nucleus. There's a lot of stars in them. They contain old stars only. They do contain hot extra emitting gas and little or no cool gas and dust. They've had no significant star formation during the last 10 billion years or so, and stars have random orbits in 3 dimensions. So elliptical galaxies and the halos of spiral galaxies are kind of similar. They have the same kind of stars. They have the same kind of orbits. So there's a lot more of them in elliptical galaxies. And the hot gas is missing in the halo. Irregular galaxies have no obvious structure. Two galaxies often have an explosive appearance. Irregular galaxies contain both young and old stars. They're very abundant in gas and dust. They tend to have very vigorous ongoing star formation. And the stars and the gas all have regular orbits. Now, Hubble's tuning fork is a convenient way to remember the galaxy classifications, but it has no deeper meaning. So there's nothing special about this tuning fork other than it's a convenient structure to organize our classifications. So let's look at some patterns in galaxies. So we can look at color or temperature and luminosity or brightness. Basically make something like an HR diagram, but for galaxies. We see small blue galaxies that have lots of young stars, large blue-white galaxies that have active star formation. We have smaller galaxies without star formation, tend to be companions of larger galaxies, and the largest galaxies are giant ellipticals without much star formation. So spiral galaxies are often found in groups of galaxies, up to a few dozen galaxies per group. For example, we are in what is known as the local group, because sometimes scientists are not very creative in their naming. And in the local group, there's about 50 galaxies, 50-ish galaxies. Three big ones, the Milky Way, Andromeda, and M33. And then a bunch of little ones. So there's a bunch of little ones orbiting Milky Way, a bunch orbiting Andromeda, a number orbiting M33, and a few scattered about. Now, elliptical galaxies are much more common in huge clusters of galaxies that can have hundreds to thousands of galaxies. And in these huge clusters, we tend to find more ellipticals in the middle and more spirals at the edges, which implies that maybe spirals are less, are a little more delicate. That structure can be disrupted in collisions more easily, while the elliptical structure is more stable. So if there were spiral galaxies in the middle, they got destroyed, basically. Or they whacked into each other and merged to form elliptical galaxies or something. But there are these galaxy clusters with thousands of galaxies in them. But yeah, there we tend to find ellipticals in the center, and the few spirals that are in them tend to be around the edges. Galaxies are classified by their appearance into 5 types: spiral, barred spiral, elliptical, irregular, and lenticular. And each of these types is divided into subclasses. And galaxy evolution is believed to be caused by collisions between galaxies, causing them to merge together. So how can we determine the mass of a distant galaxy? Well, how do we find mass in astronomy? Generally with Kepler's third law. We can do this. What we could do is we could say, okay, the various stars in this galaxy are orbiting around the galaxy. We can use Kepler's third law to figure out the mass contained within. So we can look at the rotation of various stars. We can look at the rotation of, you can measure the rotation of objects in the galaxies. We can measure the broadening of spectral lines in the elliptical galaxy, which tells us about the orbits. And what we see, if we look at, say, a spiral galaxy, this dotted line is what we would expect to see from the stars we see. If we look at the stars, we see this much mass roughly. We expect to see something like this dotted line. What we actually observe is this line. This is a problem. This is for M33, which is another spiral galaxy in our local group. There seems to be much more mass in galaxies than what we see. Something like 80% of the mass in galaxies is invisible to us. So let's talk about the masses of galaxies. We can measure the mass of galaxies. ellipticals have the biggest range of size and mass. Again, the very biggest galaxies and the very smallest galaxies are elliptical galaxies. Irregulars tend to be smaller than spirals on average. Yeah. So spiral galaxies have masses from about 10 to the 9 or a billion to 10 to the 12 or a trillion times the mass of the sun. They have diameters from around 15 to 150 light years across. 1,000 light years across, 15 to 150,000 light years across. Yeah, those numbers make a lot more sense. Sorry. So like the Milky Way is something like 50,000 light years across, if I remember correctly. It's about in the middle of that. Their luminosity is about 10 to the 8 to 10 to 11 times the luminosity of the sun. They have a mixture of old and young stars. They have gas and dust for interstellar matter. And if we look at the mass to light ratio for the visible part, we see 2 to 10 times as much mass in the visible part than we see the light we would expect. Now, we would expect to see something on the higher end. You know, we don't expect this to be 1, because the mass to light ratio is based off the mass and luminosity of the sun. So we'd expect there to be about some amount that's not emitting light, but 2 to 10 times. And then the mass to light ratio for the total galaxy is about 100. We'd expect something in the 5-ish range or something. Ellipticals have a mass from around 10 to the 5 to 10 to the 13 masses of the sun. Their diameter ranges from around 3,000 light years to more than 700,000. Their luminosity goes from about 10 to the 6 to 10 to the 11 times the luminosity of the sun. They primarily only have old stars. They have almost no dust and little gas, and their mass to light ratio in the visible part is 10 to 20. You expect it to be higher than in spirals because they have older stars, which generate less light for their mass. And the mass to light ratio for the total galaxy is again about 100. Irregulars are 10 to the 8 to 10 to the 11. In solar masses, 3,000 to 30,000 light years across. The luminosity varies from around 10 to the 7 to 2 times 10 to the 9 times the luminosity of the sun. There's a mixture of young and old stars. There's a lot of gas. Some have little dust, some have a lot of dust. Their mass to light ratio in the visible part is about 1 to 10. And we can't really easily measure the mass to light ratio for the total galaxy because their orbits are too irregular. The mass to light ratio is a way to compare the mass of an object to the luminosity of the object. And it's, the sun has a mass to light ratio of 1. So we would expect galaxies to have a mass to light ratio of more than 1, because the sun, we're using the sun as sort of our base. So it's the mass in solar masses divided by the luminosity in solar luminosities. A galaxy we would expect to have a mass to light ratio of more than the sun because there's gas and dust and other stuff that's not emitting light and dimmer stars, things like that. So we'd expect something more than 1. Low mass stars contribute a lot of mass, but very little light, so they have a large mass to light ratio. High mass stars contribute a lot of light relative to their mass. They have a small mass to light ratio. So young blue stars have small mass to light. Old red stars have a large mass to light. So a galaxy's mass to light ratio is the sum of mass to light ratio for the objects that it's composed of. Young galaxies have a mass to light ratio of around 1 to 10. That's what you'd expect, and old galaxies would have 20 to 30. But if we look at the entire galaxy with that mass curve, we see that there's an extra, the total mass to light ratio is something like 100. So it's 80 to 90% of the mass we're not seeing. So these ratios apply to the inner parts of galaxies. While most of the matter in galaxies is this invisible dark matter, it has a lot of mass and no light. So it has an extremely high mass to light ratio. And all galaxies seem to have some amount of dark matter. Galaxies with significant amounts of dark matter can have mass to light ratios in excess of 100. And understanding dark matter will be essential to our understanding of galaxies and the universe, because it seems the structure formed in dark matter before it formed with regular matter, and regular matter accreted onto the dark matter. So basically all of galaxies are sort of dark matter lumps that regular matter was attracted to by gravity. Question?
How would be created?
We don't know. We don't know what dark matter is. I mean, it formed in the beginning of the universe at some point. But since we don't know what dark matter is, we don't know how it was formed. A lot is unknown about dark matter. Mostly we know that there's something there, it's dark, and it's most likely some exotic subatomic particle that barely interacts with stuff. Like that's the only thing that fits with what we observe. But we don't know what kind of particle it is. So we don't know when in the birth of the universe it formed. We have a decent idea of when it would have stopped interacting with the rest of the universe and started to form its own structure while regular matter was still interacting and being hot and evening itself out, which we'll get to in a later chapter. But basically what happened was universe formed. Among the stuff that was formed was dark matter. And early on, everything was interacting with everything else, creating and destroying itself. But then the most likely suspicion is that when the weak force separated from the electromagnetic force, because the various forces used to all be merged and then they separated, dark matter separated out, and so was able to start interacting gravitationally and forming structure, while all the stuff interacting electromagnetically kept evening itself out because it was still interacting and hot, basically. And that structure formed in dark matter, and then regular matter was able to condense on that and form structure very quickly in the early universe. So one of the reasons we know dark matter has to be there and certain properties about it is because the structure of the universe we saw formed very quickly, faster than it could have without her. But we'll talk about dark matter in a lot more detail later. So in order to figure out the properties of galaxies, we need to be able to measure distances. So we need to figure out where galaxies are, how far away they are from us. And part of that is because we want to figure out how old they are. Like what part of the history of the universe are we looking at? So we can't use parallax for galaxies. They're too far away. And only in the closest galaxies can we resolve individual stars. Now, in the closest galaxies, where we can resolve individual stars, there are variable stars called Cepheids. This is how we determine the distance to the nearest galaxies. We could use a period luminosity relationship to determine distance. Basically, these are variable stars. They're at a stage in their life where they vary in brightness over time. And it turns out the rate that they vary in brightness is tied to how bright they are. And that means if you know how bright something is, if you have some way of knowing how bright something is, you can figure out how far away it is. So Hubble did this for Andromeda in the 1920s to determine that it wasn't part of our galaxy. This Cepheid variable star method of measuring distance only works for the nearest galaxies, because you have to be able to distinguish individual stars. Now, galaxies are the core of modern cosmology. There are other methods that we can use to determine more distant galaxies. There are other things we know the brightness of. The one we use for the longest distances and has been in many ways the most successful is type 1a supernova. So white dwarfs exploding as they collect enough mass to gravitationally collapse and undergo a massive fusion explosion. Well, those are all identical objects blowing up. They're all white dwarfs of 1.4 solar masses simultaneously undergoing carbon fusion. So they all have the same luminosity. So whenever you see one of these supernovas, their brightness tells you how far away they are. So you can identify how far away the galaxy is.
Determining the distances of galaxies is a challenging task that relies on a chain of methods shown in this schematic diagram. Notice that each arc represents a distance 10 times as far as the prior one, and labels along the top show some of those distances. The chain begins with radar measurements of the distances to other planets in our solar system. Applying a little geometry to those measurements accurately tells us the Earth-Sun distance. Once we have an accurate Earth-Sun distance, we can use parallax to make accurate distance measurements for relatively nearby stars. For larger distances, we generally rely on classes of objects known as standard candles because they have known luminosities. This figure shows the basic idea. We see 3 street lamps that all put out the same amount of light, but differ in apparent brightness because they are at different distances. The farther away the lamp, the dimmer it appears, in accord with the inverse square law for light. Therefore, if we know the distance to the nearest lamp, we can determine the distances of the others. Several types of astronomical objects can serve as standard candles. One of the most important is a class of stars known as Cepheid variable stars, or Cepheids for short. Cepheids follow a period luminosity relation, in which a Cepheid's luminosity is directly related to the period of time over which its brightness rises and falls. For example, if you find a Cepheid with a period of 30 days, you know that its luminosity is about 10,000 times that of our Sun. We know the true luminosities of Cepheids from those with measurable parallaxes within our own Milky Way. We can then determine distances of other galaxies by observing Cepheids within them. We use the period luminosity relation to determine the Cepheid's luminosity, then calculate its distance from its apparent brightness and the inverse square law for light. Beyond the distances at which we can observe Cepheids, we need even more luminous standard candles, such as white dwarf supernovae. We know the true luminosities of white dwarf supernovae from those that have occurred in galaxies in which we also observe Cepheids, and they are bright enough to be observed throughout the universe. We can therefore use white dwarf supernovae to calibrate a relationship called Hubble's law because it was first discovered by Edwin Hubble. As discussed in more detail in a separate narrated figure, Hubble's law tells us that the recession velocity v, at which a galaxy is moving away from us due to the expansion of the universe, is equal to Hubble's constant times the galaxy's distance. We can measure any galaxy's recession velocity from its redshift, so Hubble's law then allows us to determine its distance. For example, a galaxy with a recession velocity of 11,000 kilometers per second is at a distance of approximately 500 million light-years. Nowadays, most of the distance measurements we make of galaxies come from Hubble's law.
Yeah, Hubble's law is the most generally useful tool, but you have to calibrate it. And it's basically calibrating from point dwarf supernova. So within the solar system, yeah, we can make radar measurements. It turns out it's one of those things, is this whole chain building up. And the first step of this chain to getting all these distant measurements is figuring out, how far the Earth is from the sun, basically. Because you can figure out it turns out you can figure out where all the planets are relative to each other and the Earth, but you can't necessarily put a number on it. So it took a while for them to put a number on it. They figured out a way to get it for Venus, I believe, but yeah. For the solar system, we use radar measurements. This gets us a very solid value for parallax, and then we can use parallax out until we step up to Cepheids, and then Cepheids out until we step out to more distant standards, primarily white dwarf supernovae, but there's a few other techniques. There's some relationships for the luminosity of spiral galaxies and how fast they rotate and things like that. So some of the distances, the first step was we find distances within the solar system using radar, which we could measure directly. You're bouncing light off of another planet. Then we can use that to determine the distance from the Earth to the sun. Then we can use parallax to determine the distance stars out to a few hundred light years. And after that, pretty much everything we use is built off the structure of objects of known luminosity. If you know their luminosity and their apparent brightness, you can figure out their distance. The luminosity passing through each sphere is the same. The area of the sphere is 4 pi times the radius squared. So you divide luminosity by area to get brightness. So brightness is luminosity over 4 pi times distance squared. Which means with a little bit of algebra, we can find that distance is luminosity divided by the square root of 4 pi times brightness. If you know the luminosity of an object and its brightness, you can figure out its distance. So a standard candle is an object whose luminosity we can determine without measuring its distance. So most of the time we're using brightness and distance to figure out luminosity. But sometimes you want to find distance and you know the luminosity. So standard candles are things we just know how bright they are. So an example of this is that street lamps can serve as standard candles because they all have the same luminosity. So the nearest one appears brightness. This one is twice as far away, so it's a quarter as bright. This one's 3 times as far away, so it's a ninth as bright. We can do this in space. So Cepheid variables allow measurement of galaxies out to about 25 megaparsecs away. Most galaxies are further than 25 megaparsecs away. So we need new distance variations to figure out how to figure out the distance to further galaxies. It turns out there's something called the Tully-Fisher relation, where the rate of a galaxy's rotation speed, which can be measured using the Doppler effect, is tied to its luminosity. So the speed that spiral galaxies spin at is associated with how bright they are. Also, type 1a supernova all have the same luminosity, as the process by which they happen doesn't allow for much variation. All 1.4 solar masses of white dwarf collapsing and undergoing sudden fusion. So what's a standard bulb or a standard candle? They're objects that have the same luminosity, so the differences in apparent brightness depend only on the distance. So we know the luminosity once the object is identified. This means when we measure apparent brightness, we get distance. Cepheid variable stars are very luminous. They're in this strip of the HR diagram. And the luminosity is associated with the period that they vary in. So their luminosity varies. So this Cepheid variable has a period of 50 days. And the light curve of the Cepheid variable star shows that its brightness alternately rises and falls over a 50-day period. The period of a Cepheid variable star is associated with its luminosity. So the longer the period, the brighter the star. So if we find a Cepheid with a measured period of 30 days, the red curve tells us that its luminosity is about 100,000 times the luminosity of the star. So Cepheid variable stars with longer periods have greater luminosities. But there's a relationship, so you can almost figure out what the luminosity should be for any Cepheid variable star. And for the most distant galaxies, we use white dwarf supernovae. White dwarf supernovae can also be used as standard candles. Supernovae are incredibly bright, so we can see them from very, very far away, anywhere in the universe, really. And white dwarf supernovae are all basically identical, so they all have the same luminosity. And the apparent brightness of a white dwarf supernova tells us the distance to a galaxy up to about 10 billion light years. And so, and 10 billion light years away, that's like 10 billion years into the past, and the universe is only about 13 billion years old. So type 1a supernovae are used as a standard bulb. All type 1a supernovae form from the same object, a 1.4 solar mass white dwarf star in a binary system. All of them should therefore reach the same peak luminosity, because they're all basically identical. Question?
Like they're like infinite energy.
Well, it's unknown whether the universe is infinite or not. There's a limit to what we can observe. So there's a limit to the size of the universe. That's the observable universe. It's how far away light can reach us from the beginning of the universe. There might be an edge beyond that, but we don't know. So this is sort of getting into the area of where people really don't know and kind of can't know, because we're limited to how far we can see. So the universe is finite in time. We don't know if it's finite in distance or not. But we are limited in what we can see by only so far away can light reach us, because light takes time to travel, and the universe has only been around for 13.8 billion years. Something like that. So light, all the light that the most distant things we can see took about 13 billion years to reach us. So these can be detected out to 8-10 billion light years away, and they're important for determining distances and understanding the evolution of the universe, and figuring out things like Hubble's law, which is the primary way to measure distance based off the expansion of the universe, because the universe is expanding. So the luminosity of a spiral galaxy is related to its rotation rate. A more luminous spiral spins faster. Lenticular galaxies have a similar relation, but with a slightly different luminosity. You can measure the rotation speed through the 21 centimeter hydrogen line and use this to determine luminosity and therefore distance. This is limited to spiral and lenticular galaxy stuff. And the error bars are kind of biggish, as you can see here. But any rotating object causes a broadening of lines because of the Doppler shift. One side is approaching you and one side is receding. So the side that's approaching you is at a slightly higher frequency, shorter wavelength. The side that's receding is at a slightly lower frequency, longer wavelength. And so that spreads the line out, and you see a wider line. And so you can use that to figure out how fast things are rotating. So the masses of galaxies can be determined by using Newton's modified version of Kepler's third law. The mass to light ratio compares the amount of mass it contains to the amount of light it emits. The mass to light ratio for the sun is 1. And the distances to galaxies can be determined using Cepheid variable stars for nearby galaxies, or standard bulbs like type 1a supernova. Here's the distribution of galaxies within about a megaparsec of the Milky Way. So these are some nearby galaxies. Here's the handful of galaxies near us. The nearest galaxy to us is the Sagittarius dwarf galaxy. There's the Ursa Minor dwarf, the Draco dwarf, Sextus dwarf, the small and large Magellanic Cloud, the Flomax dwarf, Carrion dwarf. These are all the galaxies that are basically orbiting around the Milky Way. They're all small. And then there's two other big galaxies. Andromeda and M33 are the other two big galaxies in our local group. This is the local group. So there's 3 spirals in this group, the Milky Way, Andromeda, and M33. These and their satellites, it's about 50 odd galaxies. The number keeps going up over time, so there might be some variation in my slides. We find small dim ones that we hadn't found before, is the local group. And such a group of galaxies held together by its own gravity is called a galaxy cluster. The local group is a small galaxy cluster. There are galaxy clusters with thousands of galaxies. And then there are sort of superclusters, which are clusters of clusters. A nearby cluster, large cluster, is the Virgo cluster. It's much larger than the local group. It contains about 3,500 galaxies. There's M87, M86. These are really big galaxies. I believe M87 is the one that we imaged the black hole with. So one of the things that was discovered, interestingly, is that the universe is expanding. Mentioned Hubble's law. Well, Visto Sulfur at Lowell Observatory from around 1912 to 1932 observed the spectra of dozens of these spiral nebulae. These were actually galaxies outside of our galaxy, but people didn't realize that. And he found that most of these exhibited large redshifts. So they were going away from us quite fast. And then in 1927, George Lemaitre published a paper suggesting an expanding universe that was consistent with general relativity, and used as evidence Sulfur's observations. So he solved the equations of general relativity, found we could have an expanding universe. Einstein, in fact, that was a solution, and that Sulfur's observations were evidence for this. But the whole thing was not put together until later by everyone else. So universal reception, pretty much all galaxies outside of our local group. So there's a few nearby exceptions, but otherwise all galaxies have a redshift. They seem to be moving away from us. And if we look at how far away they are and at the redshift, we find that the further away they are from us, the faster they're moving away from us. And this is consistent with an expanding universe. So this is what's known as Hubble's law. So Hubble took those observations by Lowell, but also was the first person to realize that these were in fact galaxies. He was the guy who started to measure the distance to these objects with large redshifts. And was able to put together that these were galaxies, and these galaxies were all moving away from us. And there was a very clear relationship where the further away from us they were, the faster they were moving away. In a linear manner.
Hubble's law expresses a relationship between distance and recession velocity that can be used to estimate distances to very distant galaxies. Scientists have calibrated this relationship by measuring the distances and recession velocities for many galaxies. Here are some sample data. Each galaxy's distance has been measured using a standard candle technique based on the apparent brightness of a white dwarf supernova that has exploded within it. Each galaxy's recession velocity, which is the speed at which it is moving away from us due to the expansion of the universe, has been determined from the measured redshift of lines in the galaxy's spectrum. The best fit straight line represents Hubble's law. The dashed lines represent the uncertainty range, meaning that the data are consistent with the true law being anywhere between them. Notice that if we go 1,000 million or 1 billion light years of distance along the best fit line, the recession velocity increases by 22,000 kilometers per second. In other words, the slope of the best fit line tells us to expect the galaxy's recession velocity to be larger by 22 kilometers per second for every 1 million light years of distance. We can use Hubble's law to estimate distances to galaxies for which we do not have standard candle measurements. Suppose a galaxy has a recession velocity of 20,000 kilometers per second. To find its distance, we look across to the line for Hubble's law and down to the distance axis, which gives an answer of about 910 million light-years. Now consider this question. Suppose you obtain a spectrum of a distant galaxy, and, from its redshift, you measure that it is receding from us at a speed of 33,000 kilometers per second. What does Hubble's law predict for its distance? Is it 33,000 light-years, 33 million light-years, 1.5 billion light-years, or 30 billion light-years? The answer is C. To see why, we first look at the vertical axis to find the recession speed of 33,000 kilometers per second. We go across to see where this speed is found along the best fit line, then down to see that it corresponds to a distance of 1,500 million light-years, which is the same as 1.5 billion light-years. We can also state Hubble's law with a simple equation. Velocity equals Hubble's constant times distance. If we divide both sides by Hubble's constant, h0, we find that distance equals velocity over Hubble's constant. We can use this equation to calculate a galaxy's distance from its recession velocity, and we'll get the same answer that we get using the graph.
So Hubble was the first person to really put together all this thing, these redshifts and the distances. In 1931, he published a paper relating the velocity of precession of galaxies to the distance. This is his data from 1929. These are much closer galaxies. You can see here we have that small number of galaxies that are actually approaching us. And then when he extended it to further galaxies with massive, this is data from 1931, he got much better. You can see the trend is much clearer. So Hubble's law says velocity that a galaxy is proceeding at is equal to a constant, which we call Hubble's constant times distance. And that constant seems to be more or less the same throughout the universe. So if we can determine Hubble's constant, the slope of the line, we can determine the distance to any galaxy that we can get a spectrum of, and it's beyond our local region of space. Our current estimate of Hubble's constant is about 22 kilometers per second per million light years. You can also write it in terms of parsecs. 72 kilometers, 70 odd kilometers per second per megaparsec. So a galaxy a billion light years away would be receding at a speed of 22 kilometers per second. A galaxy 10 billion light years away would be receding at 10 times 22 kilometers per second, or 220 kilometers per second. So if you want to figure out how far away a galaxy is, you measure its redshift, you figure out how fast it's going, and then you divide by Hubble's constant. So yeah, the value of Hubble's constant is about 70 kilometers per second per megaparsec, or 22 kilometers per second per million light years. Recessional velocity equals Hubble's constant times distance. And measuring distances using Hubble's law works better the further away the object is, because the random motions forward and back that galaxies have basically get overwhelmed by the recession. So Hubble's law is most useful at the largest distances. And one of the questions people ask is Hubble's constant actually constant? Because one of the things is that looking out into space is like looking back into time. And using this to determine distances means that we are assuming Hubble's constant was the same 10 billion years ago as it was today. So what might cause this to change? Well, if we consider gravity, galaxies are all pulling on each other, and therefore should slow down the universal expansion rate. If gravity were the only force involved, galaxies should have been moving faster in the past and are moving slower now. But if we had some other force, it might do other things. This is a field of active debate. There's right now a whole bunch of really active debate about whether certain things to do with this were flawed or not. So a uniformly expanding universe. So what does it mean for expansion? So the Copernican principle is that we aren't any special point in the universe. But you might say, it seems like we're special, everything's moving away from us. If all galaxies are moving away from us, does that mean we're the center? And the answer is no. Because the universe is expanding, the space between everything is getting bigger. Everybody sees everything expanding away from them. So an example of this, a one-dimensional example, is ants on a ruler. If we have ants on a ruler and we stretch that ruler out, let's say it was made of rubber, an ant at a 2 centimeter mark will see all other ants moving away, more ants, distant ants moving away faster. But an ant at the 7 centimeter mark will see the exact same thing. So here at the 2 centimeter mark, you see all these ants moving away from you, with the more distant ants moving faster. But at the 7 centimeter mark, all the ants are moving away from you, with the more distant ants moving away faster. A three-dimensional example is raisin bread. An observer on any raisin would see all the other raisins moving away further away, the more distant raisins moving away faster. Raisin bread expanding as the dough rises, for example. Now, what's happening is the space between galaxies and galaxy clusters is expanding, not the galaxies or the clusters themselves. The galaxies don't get bigger, planets aren't getting further apart. In reality, there's no egg or center to the universe, as far as we can tell, which is different from our examples. They have an actual edge. But what's happening is space itself is expanding and galaxies are carried away as it expands. And there's a lot of debate what might be going on a larger scale, but we really don't know. And one of the fun things is, if you have an expanding universe, well, you can run that expansion backwards and figure out how old the universe has to be from. So, what do these distance measurements tell us about the age of the universe? Well, if we find Hubble's constant, everything is expand and assume that the expansion is just constant. Then if everything is expanding at 22 kilometers per million light years, well, we can sort of run that expansion backwards. And it turns out all you really need to do is just take Hubble's constant as 22 kilometers per second per million light years. This is a distance divided by time divided by distance. So this actually ends up just being in units of 1 over time. It turns out if you clean up all the units, 1 over Hubble's constant is a decent estimate of the age of the universe. So Hubble's constant tells us the age of all the universe because it relates velocities and distances to all galaxies. So the idea is that the distance traveled is just going to be the time it's had to travel, the age times the speed it traveled at, the velocity. So age is distance over velocity, but distance over velocity is just 1 over the Hubble's constant. And so 1 over Hubble's constant is actually an estimate of the age of the universe. And if you want to work out all the unit conversions, you'll get something around 13 and a half to 14 billion years. So the expansion of the universe was first seen over 100 years ago. Edward Hubble formalized this into Hubble's law, relating the velocity of an object to its distance. And the expansion is an expansion of space, not a direct motion of galaxies. It's only the space between galaxy clusters that is expanding. And to our best understanding at this point is that the expansion is not perfectly uniform. And in fact, it seems to be accelerating, though there is currently a whole bunch of debate going on about that right now. But working out whether or not it's accelerating or exactly if it is accelerating, how much is really tricky. So there's some debate that some of the values that we've gotten might not be correct. So let's move on to other types of galaxies, active galaxies. We talk about normal galaxies. Active galaxies are galaxies that are pumping out a whole bunch of extra light. So there's two primary differences between normal and active galaxies. Active galaxies are more luminous, they're much brighter, and active galaxies emit more non-stellar radiation. They emit radiation that doesn't look like what we would see from stars. So it's not just thermal radiation like you'd see from stars. And it turns out that all active galaxies, to our best of our understanding, have the source of this extra luminosity and non-stellar radiation is what's known as an active galactic nuclei, where the center at the activity in the nucleus of the galaxy is what makes it active. So it's actually activity around the very center of the galaxy. So it's associated with the supermassive black hole in the center. So about 20 to 25% of galaxies don't fit well into the Hubble scheme. They're far too luminous. So here's a normal galaxy. It looks like a black body curve. It's got this luminosity. Here's an active galaxy. You can see it doesn't look like that black body curve. It's much flatter. And it's much brighter. Such galaxies are called active galaxies. They differ from normal galaxies in both the luminosity and type of radiation they emit. So they're brighter, and their emission of radiation is not the same as a normal galaxy. The radiation from these galaxies is called non-stellar radiation because it's not what we see from stars. And many luminous galaxies are experiencing an outburst of star formation, probably due to interactions with a neighbor. These are called starburst galaxies. And they're not what we're going to be talking about with active galaxies. The galaxies we're discussing now are those whose activity is due to the events occurring in and around the galactic center. So some examples are things like a Seyfert galaxy, which is a spiral galaxy with an unusually bright nucleus, like you can see here. There are radio galaxies that have an excess of radio emission and often jets of material, and blazars, which are the compact centers of elliptical galaxies. Yes?
Not unusually bright.
Because it's much brighter than you would expect from a normal spiral galaxy. So this, your normal spiral galaxy, the center wouldn't be nearly this bright. It's putting out a lot more light than you would expect. So it's unusual. So Seyfert galaxies, radio galaxies, and quasars. So Seyfert galaxies look like normal spiral galaxies, but their cores are thousands of times more luminous than a normal spiral galaxy's cores. So they're the center of these galaxies is way brighter than a normal spiral galaxy. And that light from the cores of these very rapidly. And that indicates that the core must be extremely compact. So one of the things that you can do is it takes light to cross time to cross across an object. So you can get an estimate, or you can get a limit on the size of an object by how fast its brightness varies. Because, if the brightness of an object suddenly increases, the light from the near side and the light from the far side are going to take a different amount of time to reach you. And that's going to stretch out the variation. So the fact that we see rapid variations in the luminosity of these Seyfert galaxies lets us know that the objects in question have to be very small. So, these are varying on the scale of like less than a year. Or on the scale of a year, which means they have to be on the scale of a less than a light year. Yeah.
Is the core one object or is it multiple objects? And if it's multiple objects, is there like empty space in between?
So the core is, we're gonna get into that, but the core is basically for these active galaxies, the active core is, so the core is just, when you're talking about core, it's just the center of the galaxy. But the active galactic nucleus, the thing that powers it, it's the supermassive black hole and the material falling into it. So, like in our galaxy, we have a supermassive black hole, there's stars orbiting in it and stuff. That whole structure around it, you could call it the core. But we can figure out that the thing that is generating light here has to be very small because it's varying in brightness so quickly. So we can basically work out that it can't be stars. So the core, if the core was multiple objects, yes, there could be empty space in between them. But to the best of our understanding, it's primarily a black hole and the accretion disk around the black hole. So that was a Seyfert galaxy. This is a radio galaxy. They have an excess of radio emission. They have way more radio waves being emitted than you would expect. They often have large jets of material being emitted over enormous, these are intergalactic scale structures being shot up. And then blazars are the compact centers of elliptical galaxies. So these are radio galaxies. They emit very strongly in the radio portion of the galaxies. And then in radio waves, we may see these massive lobes that are visible to optical telescopes that are perpendicular to the plane of the galaxy. So the galaxy is sort of a flat disk that's spinning and shoots out huge jets of material. And radio galaxies can also be core dominated. We think core dominated radio galaxies are just when the jets are facing us. Core dominated and radio lobe galaxies are probably the same phenomenon, either viewed from the side or viewed towards the galaxy. We see a core dominated galaxy instead of a lobe radio galaxy. Probably the same thing, just is the jet coming at us or is the jet perpendicular to what we see? And many active galaxies have jets, and most show signs of interactions with other galaxies. And lastly, we have blazars, which are the compact centers of elliptical galaxies that are active and very bright. And quasars are what were called quasi-stellar radio sources. These were radio sources that were observed. They were very bright. They looked kind of like stars, but their spectrum didn't make sense. And they were mysterious objects. Their spectral lines didn't match with any known on Earth until in 1963, Martin Schmidt noticed that the emission lines in the spectrum of quasar 3C273 had the same spacing as hydrogen lines. And then he worked out what the redshift would be for this. They were extremely redshift. It was receding at 15% of the speed of light. And Hubble's law tells us this object had to be incredibly distant. And in fact, quasars are some of the most distant objects we see. They're, they could be billions of light years away. Most of them are around 10 billion light years away. They're quasi-stellar objects. They're star-like in appearance, but they have very unusual spectral lines. This is quasar 3C273, and this is a relativistic jet produced by its central black. So quasar spectra were normal, but they're extremely redshifted. So this is the spectrum of that quasar. This is a lab comparison spectrum of hydrogen. You can see these are the lines that match up. They're just massively redshifted. And the highly redshifted spectra of quasars indicate very large distances, and for brightness and distance, we find the luminosities of these objects are, some of them are 110 to the 12 times, more than 10 to the 12 times the luminosity of the sun. And the variability of this luminosity shows that all this comes from a region smaller than the solar system. So you have something smaller than the solar system putting out more light than a lot of galaxies put out, which is crazy. And so what are these? They only appear like stars because they're so far away. They're actually the nucleus of a very distant galaxy. Millions are now known. All show redshifts, and the largest velocities are around 96% of the speed of light. And we are, I guess we have a little more time. And this is the first object to be identified as a quasar. It has a luminosity 1 trillion times that of the sun. And quasars are parts of galaxies. Since galaxies obey Hubble's law, so should quasars. And most of them are 10 billion light years, 10 billion or more light years away. None of them are nearby. It seems like this is a phenomenon from the early universe, that basically all of the quasars, most likely what happened is that being a quasar was something that could happen with a galaxy when it was young. And at this point, all of the quasars that existed near us have basically exhausted the fuel for being a quasar. Whatever form these only existed long ago, we're seeing some part of the early history of the universe. And solving the spectral problem introduces a new problem. Quasars need to be some of the most luminous objects in the universe to be visible over such enormous distances. And I think I will stop there for today. So I'll see you all next week. And yes. And I will end the meeting. So see you all next week.